The proton NMR spectrum for para-ethyl is shown below. Which signal correlates to the indicated hydrogen atoms? So the hydrogen atoms that we are focusing on in this question are these two hydrogens here at the benzylic position. So those are benzylic hydrogens. So before we get around to answering the question, let's talk in general about proton NMR and the four key pieces of information that you should get from it. So the number of signals in the proton NMR tells you about the number of different hydrogen atoms that you have in your molecule. So we have 5 signals in here. That tells us we have 5 sets of hydrogen atoms in our molecule. The chemical shift, which is this parts per million scale on the bottom, that tells us about the environment these protons are in. The integration will tell us how many hydrogens are causing the signal. So this is the first thing I'd like to focus on for answering this problem. We see that we have 2 hydrogens. So we expect that our integration here is going to be for 2 hydrogens. And unfortunately, we have 4 peaks that all have 2 hydrogens. So the only one that does not is this 3 hydrogen triplet, which corresponds to this methyl group at the end. 3 hydrogens, because there are 3 hydrogens for that signal. But that's not one of the options. So the options that we have all have 2 hydrogens in them. So the first thing that I would do to narrow this down is I would look at the chemical shift and think about whereabouts I would expect to see a benzylic proton show up. So benzylic meaning that it is next door to that benzene ring. And so somewhere around 2.5, give or take, seems reasonable. So that's definitely got me leaning towards this peak at 2.6. But let's talk more about the regions of the spectrum before we get into that. So these 2 hydrogens here, I would not consider for benzylic hydrogens because these are really firmly in this area that I would consider to be the aromatic region, where we have aromatic protons show up. And this 3 hydrogen triplet down here is very much in that aliphatic region where you'd expect to see hydrogens on an alkane chain. So really we'd be looking at these 2 signals here, so really between A and B. And a key thing to distinguish these, the chemical shift is pretty clear that it's this one, but the other key information here would be that this is a quartet. So that splitting tells you about the adjacent hydrogens. So if we look at these 2 hydrogens, they are going to be adjacent to those 3. So we have adjacent hydrogens, so 3 adjacent hydrogens. And the rule for splitting of a signal is n plus 1. So the n is that 3, it's your number of neighboring hydrogens. So we are saying that 3 plus 1 is 4. So we would expect that this signal would be a quartet. So now that we've got the appropriate integration, 2 hydrogens is around where we'd expect it to be. We see the splitting also matches. That's really clear that this is signal A, okay? But let's go ahead and while we have this, let's see if we can assign most of the hydrogens here. So we've got 2 sets of equivalent hydrogens in the aromatic region, and that's because we have a plane of symmetry. It kind of runs right down that ring. So these 2 hydrogens would be the same as each other. The other 2 aromatic ring hydrogens would also be the same as each other. So these are the 2 sets of protons that we're seeing here in the aromatic region. Okay, so those are our aromatic protons. I want to point out that this sort of splitting pattern, a 2 hydrogen doublet and a 2 hydrogen doublet, is really indicative of a benzene ring that is substituted 1,4. So that 2 hydrogen doublet often happens when you have this 1,4 pattern. So we say these are different substituents, X and Y. So these 2 hydrogens would be the same and these 2 hydrogens would be the same. Okay, and the total number of hydrogens matches the total number of hydrogens on the ring. So if you had an unsubstituted benzene, so unsubstituted benzene, just benzene itself is C6H6. So looking at the number of aromatic hydrogens, right? So we can say unsubstituted benzene has 6 hydrogens. This molecule has 4 in that aromatic region. So this tells us 2. Now what's 2? It's the number of substituents on the benzene ring. So that's a quick and easy bit of math we can do to figure out how our benzene ring is substituted if we weren't given a structure like we are here. Another thing I'd want to talk about here is this NH2 signal. So notice that the signal for this is the signal at around 3.4 ppm. It's really broad, and that's due to hydrogen bonding. And you might also notice that it's not split. Well, that's typical in this case. We don't have a hydrogen on the adjacent carbon. But even if we did, we probably wouldn't see the splitting. So signals that undergo hydrogen bonding, so these are going to be OH and NH signals, are often broad. And so they usually don't split or cause splitting. Okay. And there's one more thing that we can say about these OH and NH signals if we suspected, if we weren't sure between these two and we wanted to do a little chemical test, we would probably find out that this 2 hydrogen signal would disappear if we added deuterated water. And so the way that we would notate that is we would say that this exchanges with D2O. So that's deuterated water. So deuterium is inactive in the proton NMR. So seeing that disappearance tells you that you have a proton that can exchange. So that really indicates to you that this is a hydrogen attached to nitrogen or oxygen. So that would be another way that we could differentiate those 2 signals if we weren't quite sure.